Yeah. So, we are talking about this different possible configurations, meaningful configuration, and let you go one by one how they are helping us to improve the performance. So, in the next slide we will be mixing CE and CC. So, for our reference we do have the main table, we are keeping it here, and we will see that how the CE and CC will be helping us to improve the performance. To start with, let you consider CC and CCs together, and then probably we will see the CE and CC. So, we do have the basic CC configuration, and its main characteristic or main requirement is that input is at the base and output is at the collector. So, if I consider say one transistor, we do have say input we are feeding at the base of this transistor, and let me call this is Q1, and then its output it is going to the second transistor. So, we do have the second transistor here, and let you call this is Q2, and of course, the collector here and collector here, they should be connected to the main supply, better be connected to main supply. In fact, we can have some resistance also connected there, but for ideal condition we want that. And if you see their bias conditions, so we may think of that it is having a DC current here, as we can see here, and we may or may not require this DC current depending on the level of the current of the Q1 and Q2. So, if I say that if we do not have any bias current here, which means that the base current of the second transistor, it is same as the emitter current of the first transistor. If this is getting satisfied, then we do not require. Otherwise, the additional current of the emitter, in case if it is a emitter current of the transistor 1, it is higher than the required base current of the second transistor, then we may require this bias circuit. So, that is why I am just putting a dotted line. So, depending on the situation we may or may not consider, but whatever the situation it is, small signal wise you may say that for ideal current source here we may think of this is open. So, if I draw the small signal equivalent circuit, and if we are feeding the signal directly to the base base of the second transistor, then we can draw the small signal model of the first transistor, and then followed by the second transistor. Let me use that blue color just for consistency of the other diagram. So, this is the small signal model of the second transistor Q2, and this node it is connected to DC voltage, which is AC ground, and this is also AC ground, and of course, we do have the input port. So, we may say that the input signal we are feeding here. So, this is the input signal Vs. Now, if you see that different parameters of the individual transistor, we do have R pi 1, and then we do have R O 1. Likewise, for the second transistor, we do have R pi 2 and then R O 2 and this is the output node. So, primary output port it is given here. Now, what we are looking for, it is basically two things. One is the increasing the input resistance and also it is we are expecting that this will decrease the output resistance. So, let us see how this configuration or this kind of mixing it is helping to get higher input resistance. So, R in, if I consider, to get the R in, of course, we can whole circuit we can analyze, we can find what is the corresponding input current going there, and then if you take the ratio of this V s and then this I in. So, from that you can say what is the expression. Better approach or qualitative approach, it is something like this. Suppose if you consider the input resistance of the second stage, depending on whatever the load we do have here, say R L. So, we may say that this resistance looking into the base of transistor 2, it is R pi 2 plus 1 plus beta into R L. We can ignore this one, and so that is the resistance. Now, on the other hand, if you are coming to the primary input port and if you try to see what is the corresponding input resistance, you can see that we do have R pi 1 plus beta of the first transistor 1 plus beta 1, it is amplifying whatever the impedance you do have. So, even if you are you may consider this one or you can ignore that, but whatever it is. So, 1 plus beta 1 it is multiplying this R O 1 plus whatever the resistance you already have obtained here. So, in summary, so that is in fact the input resistance of the entire circuit. So, in summary what we can say, of course, this beta it is the second transistor beta. So, we should write beta 2. To summarize this input resistance, it is R pi 1 plus 1 plus beta 1 into okay. So, this should not be plus, it should be rather in parallel with whatever you do have. So, that is R O 1 in parallel with this part. And if you consider the dominant terms, of course, this will be dominating 1 plus beta 1 multiplied by R O 1 in parallel with this one 1 plus beta 2 into R L. Okay. So, if it is very clumsy for you, I am writing the expression here, the final expression 1 plus beta 1 multiplied by R O 1 in parallel with 1 plus beta 2 into R L. In fact, if you ignore this part, what you can say here, it is 1 plus beta 1 and then 1 plus beta 2 multiplied by R L, which means that whatever the load resistance we are connecting here R L to the circuit, that is seen by the input signal source through this amplification of the impedance of each of the stages, namely 1 plus beta 1, 1 plus beta 2 are getting amplified. As a result, you can get really high, very high input impedance. So, the purpose of CC stage, first one, it is input impedance. So, the advantage rather we are writing here. So, the advantage here it is the input resistance So, input resistance is very high, very high. On the other hand, if you see the output resistance, and we are looking for this output resistance should be as small as possible. So, if you see, okay, so let me clear, otherwise I will not be able to explain to you. So, the same configuration, namely CC followed by CC, so we do have the CC followed by CC, and so we do have the Q1 here, we do have the Q2 here. And this is connected to VDD. The output impedance, so we know that this will be in the order of 1 by Gm, and in this case Gm of the second transistor. So, now the Gm, of course, it is function of the current. So, we do have Gm is equal to IC divided by Vt, or rather 1 by Gm it is Vt divided by IC of the second transistor. And in this case, if you see that, of course, it depends on the current. So, higher the value of this current, then we can have better situation, namely smaller output resistance. But then to support this current, in case if you are loading the primary port, then it may be a problem. But then since we do have the second transistor here, to support this high value of IC 2, we require a smaller version of this same current, namely IC divided by beta of the second transistor, which is eventually this is equal to IE of the first transistor. And to support this, we require a base current here, which is very small, namely IE 1. So, IB equals to this IE 1 divided by 1 plus beta. So, to support this large current, we require here it is the required base current is very small. So, this base current it is coming here after this amplification of 1 plus beta 1 of the transistor 1, and then we do have this beta 2 coming from the second transistor. So, what we are getting here it is the again the output resistance, because this IC we can support very high value, and then you can see that the output resistance of CC stage it is very low. Okay. So, that is what that is the advantage of having CC followed by CC. Now, let us see the other configuration, namely CE and CC. So, mixing across different configuration. So, we do have the CE stage circuit here, CE configuration, and then also we do have the CC configuration. and let us see how they can be mixed together to get the combined circuit. So, we do have the first transistor, see we do have Q1 here and its corresponding RC. For simplicity, I am not putting any emitter degenerator, we are using fixed bias configuration, and then we are feeding the signal here. And then this output, it is going to the CC stage. So, let me use different color here. Yeah. So, we do have the CC stage and the collector, it is connected to the supply, and then we may have the corresponding bias circuit or the load resistance here. So, this is the primary output port. So, as we have said that the CE stage, it is providing good voltage gain, and also it is having decent amount of input resistance, but then output resistance it is high, namely it is dominated by RC. But then if we simply cascade it with CC, so we are anticipating that the resistance coming to the output port without considering this RL. If I consider only up to this one, and if I see what is the output resistance, we are expecting that this output resistance, final output resistance, it should be much smaller than this one. So, what is the output resistance? You may recall. So, this is CC stage. So, naturally its output resistance expression, we are expecting it will be 1 by Gm of this transistor, assuming that whatever the circuit we do have here, its resistance is 0, but so this is true if the resistance of the signal source is 0. So, if I say that corresponding Rs is equal to 0, but if it is not, then 1 by Gm2, as we have discussed earlier, this Gm2 it will be getting attenuated by R pi here and whatever the Rs will be having. And incidentally, Rs is in fact close to Rc. So, I should say for Rs2 equals to Rc, what we have here, it is R pi divided by R pi plus Rc. Right. In fact, you can further simplify this expression, which is R pi plus Rc divided by Gm2 multiplied by R pi 2, which is beta of the transistor, beta 2. So, you may say that since this Rc it is getting divided by beta 2, even though we do have the R pi of the second transistor coming in series, but since it is getting divided by beta 2, this is much lower than. So, I should say this is much lower than Rc. So, what is the conclusion? The main advantage here it is, if I am having only CE, the R out it was Rc, that is getting changed to R pi 2 plus R C divided by beta of the second transistor, right. So, that makes much smaller and that is useful for the connecting a load. In fact, the not only it is just making the output resistance getting smaller and concluding in that form, we can further go and say that what is its main advantage and motive. By this, if the upper cutoff frequency earlier it was decided by say R C with R C L, in case if you are connecting a load capacitance directly there without considering C C stage, then the upper cutoff frequency it was like this. Now, this upper cutoff frequency it is getting changed to 1 by whatever the new new output resistance we do have, R pi 2 plus R C multiplied by C L and then beta 2. So, approximately if I drop this part for just for qualitative comparison, we can say that this is beta 2 times whatever earlier upper cutoff frequency we are having. So, this is the modified one if I say dash, and this is the original one. So, we can say that the bandwidth of the circuit, bandwidth of the amplifier, it is getting extended. Now, so that takes care of the output port. Similar kind of things it can be done for the input port also. Namely, if I precede this C stage by CC stage, then we can get the enhancement of the input resistance. So, in case even though whatever the input resistance we do have, namely R B and R pi, if we are not really happy with that and if you want to further increase it, then we can do that, we can mix this CC configuration before the CE stage. So, in the next slide what we are going to do, we will be having CC followed by CE. So, here again we do have the individual stages, and if we mix them together, this circuit configuration will be getting is the main transistor CE, main transistor it is in CE configuration. So, we do have the RC, and then let me call this is Q1, supply you do have the VDD, and this is the output port, and then we do have the, so let me call this is Q3 connected to VDD, and so this is the CC stage, and the input we are directly putting here. So, either we may have the bias circuit here, or depending on the situation we may put signal with a meaningful DC. So, of course, if I put bias circuit, on the other hand we can put a DC blocking capacitor, and then we can feed the signal whatever it is. And then of course, in case the emitter current here, it is entire emitter current DC current, if it is not necessary for the base of the main transistor Q1, then you may put a current sink path. So, the excess current it will be going here, the other part the base current it will be going to Q1. So, whatever it is, the input resistance of this circuit, small signal input resistance, that is our primary interest, what is the corresponding expression. So, if you see the circuit here, the impedance coming from the Q1 at the emitter of Q3, it is, we do have the R pi here. So, we can say that we do have the R pi 1, and then whatever the impedance we will be seeing here, it is this R pi 1, and then of course, we do have R naught. So, that R naught we can ignore. So, we can say that at this node we do have essentially R pi 1, and then input resistance at this point it will be R pi 3 coming from transistor 3 plus R pi 1 in parallel with whatever R O 3, though as I said you may ignore, which is getting multiplied by 1 plus beta of transistor 3. So, you can approximate this by saying that this is R pi 1 multiplied by 1 plus beta 3. So, what is the advantage we are getting here? That input resistance, this input resistance initially for this stage it was R pi 1, that got enhanced or increased to R pi 1 multiplied by 1 plus beta 3. In fact, this is very common technique, it is used for op amp. We can put this additional transistor here, which enhances the input resistance, and this is important for BJT circuit. For MOS, we know that gate resistance is very high. So, such kind of enhancement it is not required for MOS configuration, but for BJT, since R pi it is not very high, we may require the CC stage to be used to proceed with CE stage. So, we do have this C stage input resistance, it is getting enhanced by this CC stage. So, that is the advantage. So, likewise we can go for the other configuration. Let me see what are the other configuration I do have. Yeah, yeah. So, before I go to this composite configuration, I must say that so far, so we are talking about the CC and CE. We also talked about the CC and CC. So, is there any better way of analyzing this kind of circuit? Just I like to give a little notion of that. We do have the next discussion, something called composite transistor. So, let us see what does it mean. Suppose we do have say one transistor in general, say Q1, and then we do have another transistor say Q2. So, whether it is CECC or CCCC, this kind of configuration we are seeing, and say emitter of Q1, it is directly internally getting connected to the transistor 2, and as an user or as a the complete circuit designer, we may not be much interested of accessing this node. Instead, we like to access this node to feed the signal probably, or we like to access say this node to observe the signal, and or to access this node. And at the same time, we like to keep the collector of the first transistor to a meaningful voltage called say VDD. So, if you see this configuration, And of course, whenever we do have the emitter current of Q1 coming here, either the entire emitter current need to be consumed by base terminal of Q2, or we should be having some bypassing arrangement here. So, I should say if I am having say this bias VDD and this one, then whole thing. So, if these two bias is properly arranged, then whole thing it can be clubbed together and it can be considered one single transistor, where you may call this is the base terminal, this is the collector terminal, sorry this is collector terminal and this is the emitter terminal. Now, incidentally the collector and emitter terminal of Q2 it is coinciding with this, but then base terminal of Q2 it is not visible to us or user. On the other hand, base terminal of Q1 it is defining the base terminal of the transistor or the complete transistor. So, we may call this as composite transistor, and if we consider this is composite transistor, for one transistor we already have seen that 3 possible configurations are available. Now, if I call this is base of the composite transistor, and if we denote by B subscript C, this is collector of the composite transistor denoted by C subscript superscript C. So, likewise emitter superscript C. Now, can I use this entire composite transistor in different configuration? So, let us see. Suppose if I connect this circuit in say CE configuration. So, what do I have to do? Let me use some color, let me use blue color. So, for CE configuration what I have to do? I need to put a bias here, and then I need to put the signal here, and then I need to put some bias circuit here through RC, and the emitter we can connect to ground, and we call this is the output node. So, what we have done here it is composite transistor in CE configuration. Now, if I put this in CE configuration, internally what we have obtained here it is actually this is CC stage and this is CE stage. So, we can say that if the composite transistor it is in CE configuration, which is making CC followed by CE. So, likewise if I put the composite circuit or composite transistor in say CC configuration. So, for CC configuration what I have to do? I have to rather instead of connecting this to ground and the supply, I should connect to rather directly to VDD, and instead of calling this as output, we will put a resistance here and then we call this is output, and then of course, we will be feeding the signal here. So, now we obtain by this connection and this resistance here called RL, we got composite transistor in CC configuration. But then internally if you see that this is anyway it is CC. So, Q1 it is in CC and then Q2 it is also CC. So, in other words, if the composite transistor it is in CC configuration, eventually we are getting CC configuration. So, likewise this composite transistor can be connected in different configuration, and the analysis can be whatever the analysis we have done for CE and CC configuration, that can be utilized to get the overall performance of the CCCE or CCCC configuration. Okay, we will continue this one, but let me take a break and then we will get back to it. Thank you.